In this video, we will have section 5.3 from Topics in Algebra by M.ScMathematics, namely roots of polynomials. So, in this section, we will have this theorem, reminder theorem, and this lemma. Only these two that we are going to have in this video. Now, actually, the section is mainly about the uniqueness of the splitting field. Splitting field is the smallest field which contains all the roots of the given polynomial. Now, we have been telling that as for polynomials are concerned, two things are to be noted. One is it is over what. The given polynomial is over what, and where does the roots of this polynomial lie. So these two are of main concern as for any polynomial is concerned. So it is over what and where do the roots lie. So here, so the main aim is to talk about the smallest field extension in which a polynomial of degree n has n roots. So that is the main aim of this section. So for that, certain definitions, theorems, and lemmas are to be established. So in this video, we will have only this much. First, we have the definition of root of a polynomial. An element A in K. K is considered as extension of F. F is the base field and K is extension field of F. K is extension of F. So, an element A in K is called a root of f of x if f of A is 0. Reminder theorem is the first theorem in the section, which states that if f of x in fx and K is an extension, f of x is a member of fx and K is an extension of f, then for B in K, we can write our f of x as x minus b into g of x plus f of b, where degree of g of x is equal to degree of f of x minus 1. This is what we have to establish. Now, f is contained in K. K is extension of f, so we have this. And f of x in fx, and that is we are considering it's a polynomial over f means it should be a polynomial over k also. So now that we have got in k of x two polynomials, one is f of x, the other one is x minus b. So we are going to apply Euclidean algorithm to these two polynomials. So we can find g of x and r of x in k of x such that everything is not discussed in k of x. It is only here that everything is discussed. So we can find g of x and r of x in k of x such that f of x is equal to x minus b into g of x plus r of x, where either r of x is 0 or this is true. Now, if we consider this part, this is of degree 1. So this is less than, this one is less than the degree of x minus b. So being 1 and the degree is always greater than or equal to 0, degree of any polynomial non-negative. So this is strictly less than 1 means no other go, degree of r of x should be 0. So whether you consider this or this, it is a constant. So we shall take that constant as say some r. Now go to equation 1 now. In that, replace r of x by r. Now you take x as b because we want to determine what this r is. So for that we take x as b. So f of b equals, this becomes 0. So this one becomes 0. So you have just r. So your r is f of b. So replacing that in this equation, you have x minus b into g of x plus f of b. You're replacing this in equation 2, so you're getting this. So from here, degree of f of x is degree of x minus b plus degree of g of x. This is constant, so we don't consider that. So we have from here degree of g of x to be equal to degree of f of x minus degree of x minus b. So degree of g of x is degree of f of x minus degree of x minus b. So this is 1. So we have this. So we have established a reminder theorem which can be asked in section A. Even factor theorem can be asked in section A. If b in k is a root of f of x, then x minus b should be a factor of f of x. So that's what this factor theorem says. Here, what would be the remainder when g f of x is divided by x minus b? So that is remainder theorem. And here, when you have this b to be a root, this becomes 0. So that means this becomes a factor. So it's this factor theorem. Now, since f of x in f belongs to fx, that is a member of fx, and b belongs to k by the above theorem, because we can make use of this once these two are there. So you have this named as equation 1, where your g of x is from k of x. Now, since b is a root of f of x, f of b becomes 0. Therefore, equation 1 becomes like this. So whenever we have, because we know that even in integers, a divides b means this is definition, b must be equal to integer times a. So the same thing, we have already said that you can compare your z with fx, polynomials with integers. To remember all the results in z is very simple, and that can be carried out to fx. So based on that, you have x minus b dividing f of x, and this is called a factor. Now a in k is called a root of f of x of multiplicity m if x minus a power m divides f of x. So that is our next definition. And you should not have x minus a power m plus 1 dividing f of x. So if f of x, if it is a member of fx, that is, it is a polynomial over f and is of degree, and then it has at most n roots in any extension field. At most any, at most n roots in any extension. So this is our next lemma. The proof is by induction. See here, two things are to be noticed. Which gives us freedom to prove this theorem, this lemma easily. One is at most, and the other one is any extension field. Any extension field. So now we are going to prove this lemma by induction on degree. When you are applying induction method, then you have to search for numbers only. So here the only number that we could associate is only degree. So the proof is by induction on degree of f of x. If degree of f of x is 1, then f of x can be written as alpha x plus beta. Let a be a root of f of x in any extension field k. See, as such, we know what that k is. So we shall presume that let it have a root, say a in this extension field. Then replacing x by a, we have this. So from here you are getting a to be this, and you notice that both alpha and beta, see, you are considering f of x to be a polynomial. F of x belongs to fx means it's a polynomial. It's a polynomial over f. Over f, what we have said, the coefficients are from f. So here alpha is a coefficient, this is constant. So both of them are from f. So naturally, f being a field, a should be in f. So in any extension field we have mentioned here, that becomes just exactly f. Yeah, extension f is contained in f. So f is considered as an extension of f. So in this case, the lemma is true. So base case holds. This is our base case, and now we have the induction hypothesis. We have the induction hypothesis that assume the lemma to be true for all polynomials of degree less than n. Let degree of f of x be equal to n. So we are that means whenever I consider any polynomial whose degree is less than n, it will have at most so many roots in any extension field. So that is the meaning. Now we consider the two cases. In any extension we have said, so let that extension be some k. If f of x has no roots in that, you know exactly what that f of x is. You have considered some extension. right? In that extension, it may or may not have roots. See, suppose I consider this x square plus 2, say. The roots of this, you have x square, and this is x plus root 2i. This can be rewritten as x minus root 2i. So this is a polynomial over q. So it is a member of q of x. And you are considering, see, for q, this is the base field, you have q of root 2 to be an extension, and you also have q of for q of I also to be an extension, and you also have q of I comma root 2 to be an extension, and for q you also have q of root 3 to be an extension. So any extension, k is taken as any extension, means if this is my polynomial, it does not have any root here. In this extension, it does not have any root. So you have just mentioned that k is any extension. So if f of x has no roots, so this case is what we have got over here. So f of x has no roots in k, then f of x has at most n roots in that extension field. So how safe the word is C. Next case, let f of x have a root a in k with multiplicity m. Then f of x can be written as x minus a power m into g of x. That is known to us now from the definition. Now, if b not equal to a is a member of k in a is another root of f of x, then it should be naturally a root of g of x, because one root you have accounted here. So if you consider any other root, naturally it should be a root of this g of x. So so b is different from a. So when you consider b minus a power m, because g of b is 0, the product becomes 0. Now what is degree of g of x? It is n minus m. This is of degree n. F of x is of degree n, and this is of degree m plus the right hand side degree of g of x. So degree of g of x should be n minus m, which is less than n. Therefore, by induction hypothesis, g of x should have at most n minus m roots in any extension. Already we have considered k, so let us consider k. So that is why we say that this is a very safe word. And this together with the root a occurring m times gives already m roots we have said. Now that n minus m, this is at most. So you have at most n roots in any extension field. So that is the proof of this very simple lemma. So in the next video we will see this theorem, which states that if p of x is of degree n and is irreducible, then there is an extension E of f such that degree of E over f is n and p of x has a root in E. So these three parts we have to establish in that theorem. That will be discussed in the next video. Thank you.